Okay, so today we are going to talk about something called curve of growth analysis, which is actually quite important. Uh, so, of growth. So, what does curve of growth mean? So, if we have observed absorption, uh, say, whatever if you have neutral hydrogen along a line of sight, and if you have background quasar or a background continuum source, the foreground ISM or foreground gas absorbs. And suppose this is your background continuum, and you have like emission lines due to uh, foreground gas, foreground ISM. So your purpose of this sort of curve of growth analysis is to be able to infer the properties of the absorbing medium from the spectrum. Okay, so by doing this analysis, what we are going to get is something called an equivalent width. Okay, and equivalent width is basically uh, characterizing the depth or the strength of the absorption line. Okay, equivalent width or EW or W, this is denoted by W. This characterizes the strength of the absorption line. And this the peak of absorption is at the at the resonance frequency nu UL. So if you have a lower level L and upper level L, upper level U, the this nu naught or nu UL is where the absorption is the strongest. Okay, and right, and this W characterizes this strength of absorption. So um, the other thing is we don't have to have these absorption lines resolved, in the sense that uh, you do not need very high quality spectra. Uh, all you need is how much is the uh, background light removed close to the resonance frequency. Okay, so this can actually be poorly resolved. Uh, the true absorption width can actually be something like this, right? But as long as the area under the curve is the same, it has the same equivalent width. Okay, so even though the line is not well resolved because uh, your spectrometer is not that good, it does not have a very high resolution, but it can still uh, count how much energy is lost close to that resonance line. Okay, let's see. So the modeling of these absorption lines tells us about the velocity of the clouds, velocity of these absorbing clouds which are along the line of sight. Right? If the cloud is moving towards us, uh, then absorption will be at the blue side, because the absorber is coming towards us, and on the red side if it is moving away from us. So it tells us the velocity of the absorber. It tells us column density of the absorber. If there is a lot of column, if there is a lot of matter along the line of sight, the depth of this absorption will be stronger, right? And it can tell us the abundance of this gas which is doing the absorbing, right? If the gas is totally metal free, then you should not have metal absorption features. For example, the stronger the metal absorption, the higher the metallicity of this gas. And if your spectrum quality is very good, you can even sort of check if there is more calcium relative to iron and so on. Okay, so it's a very good diagnostic, this curve of growth modeling and sort of related analysis. Okay, so let's actually talk about what we have. So we have like this is, you imagine some sort of a cloud or some medium which is doing the absorbing. You have a background source, uh, and this is the observer. Okay, and sort of, this is sort of your beam, essentially, right? So this is sort of the solid angle subtended by the source, and you are like seeing it through this cloud, which is doing the absorbing. So, right. So let's write down the expression for F nu. Uh, F nu is the flux per unit frequency, right? So it's radiative transfer. You have to understand radiative transfer equation and these concepts really well, because all the information in astrophysics comes through photons as they interact with the medium. So this is flux. So flux is equal to F nu naught uh, e to the minus tau nu. So this is basically the background source, which is very bright, and it has a flux, an absorbed flux, which is F nu naught. But because of this medium, this gets absorbed, right? So this is F nu naught times e to the minus tau nu, plus this medium itself can emit, right, at this frequency. And that is given by B nu T excitation, right? So this is the source function for a thermal emitter. Which is the black body function or the Planck function times delta omega. This is delta omega, the uh, solid angle subtended by the source, times 1 minus e to the minus tau nu, right? So this is the absorption of the background bright source like a quasar. This is emission due to the medium itself, right? This excitation temperature sort of quantifies how emissive the medium is. Okay, is this clear? Right, so this is basically the simplest solution of the radiative transfer equation. Right, so you have absorption of the background and emission due to the medium. Yeah. This is the excitation temperature of the cloud. The source need not heat the cloud. If you can also have the heating of the cloud by source itself, but whatever it is quantified by T excitation. Okay, but here we are assuming that the cloud is much farther, so it is not affected by the source directly. Okay, so this is uh, emission uh, due to medium, and this is absorption of background light due to medium. Okay, let's see. Now at optical and UV frequencies, or basically, so we are actually going to do two sort of cases. One is h nu by kt much bigger than 1, right? So this is for optical frequencies. Optical frequencies, like frequency of 10 to the 14 hertz. For typical ISM temperatures, the temperature is much smaller. So h nu is much bigger than kt. The other regime that we are going to do so is h nu by kt much less than 1. So this is at low frequencies, radio and so on. So for example, this is very important. This is when we do 21 centimeter line, right? For that, the frequency difference between the ground and the excited state is very small. H nu is much less than kT, typical ISM temperature. But this is for optical lines or UV lines, such as Lyman alpha, H alpha, and whatnot. Okay. And let's see, this is the general formula, but if B nu T excitation delta omega is much less than F nu, that is the emission at a given frequency due to the foreground medium is small compared to the emission due to the background light source like the quasar, then we can actually ignore this term, right? Because this is small compared to this. So, so in that case, we have F nu equals F nu naught e to the minus tau nu. Simpler formula because all you see is absorbed background source. Okay. So a lot of times when we are doing quasar absorption spectroscopy, we are essentially using this. But quasar is an extremely bright source. So the intervening gas emission is nothing compared to the emission of the quasar. Okay. So this is called continuum, right? So this is the emission of the background continuum source like the quasar, and this is the foreground emission. And because of elements present in the ground state in the foreground, you will have absorption lines. So as I mentioned, you will have F nu by F nu naught. If you plot like this schematically, right, away from any absorption lines, this should be 1, right? Because you are not getting much absorption. But as soon as you have element, as soon as you hit an absorption line, you will have a feature like this. Right? So this is this is nu equals nu naught. This is frequency, and this is an absorption feature. So we are assuming that there is no line crowding. It's not as if you have a lot of uh, different elements absorbing at the same frequency. We are not including those complications. Okay. So what equivalent width is basically this area under this curve. What's the fraction of energy that's removed by absorption at that line? Okay, so let me actually write down. So equivalent width is equal to integration of d nu by nu naught times 1 minus f nu by f nu naught. Right, so so this is basically this area because uh, right, you can actually see this is a dimensionless area here. This f nu by f nu naught is nothing but e to the minus tau nu, right? So this factor is basically the transmitted flux. I mean, the ratio of the transmitted and incident flux. If tau nu is 0, everything is transmitted. And 1 minus transmitted flux is the absorbed flux. So this is the strength of absorption. You can actually easily see why W is the strength of absorption. It's a dimensionless number, right? Because this is dimensionless and you're normalizing it by 1 by nu naught. So it is a dimensionless number. So this is equal to integral d nu by nu naught 1 minus e to the minus tau nu, right? Now this tau nu depends on frequency, right? Close exactly at the resonance, you have highest value of tau nu, which is tau naught, and off the resonance, the absorption is somewhat smaller. And this is determined by that line profile that we talked about in the last class. Sometimes this equivalent width is also expressed in angstroms, the wavelength unit. So in that case, what you do is W lambda, you can actually call it, is just lambda naught times W. I mean, it just gives you that unit. Or you can also use equivalent width in velocity units. That's nothing but C times W, right? But the easiest is this dimensionless one because it sort of has this nice interpretation of just area under the curve. See, as I mentioned already, that this thin absorption feature and this broad absorption feature in frequency have equivalent width as long as the area under the curve is the same. Right, so it sort of quantifies total absorption due to that gas absorbing at nu naught, close to nu naught. Okay. So what is tau nu? So let me write down tau nu. Tau nu is nothing but integral of kappa nu ds. This is like radiative the equation of optical depth. Kappa nu is this absorption coefficient, right? The dimension of this is per centimeter, and the dimension of the, I mean, this is dimensionless. So if tau is much bigger than one, it's opaque. If tau is much less than one, it's sort of transparent. And this is actually also equal to kappa nu is just n sigma nu ds, or nl, nl, uh, the lower level. The higher the density in the lower level is, more absorption you will have. Right? So let me actually write down this expression and then tell how we get it. So pi e squared by MEC times FLU. This FLU we talked about in the last class. This is this oscillator strength of that transition. This Einstein's A, Einstein's B, FLUs, sigma LUs, they're all essentially, talking about the same thing. If you know one of them, others are known automatically. Okay. This is the oscillator strength. This is dimensionless oscillator strength. Okay. And then you have this column density. This is the line profile. Line profile is this thing which quantifies how absorption strength varies as a function of frequency. And then there is a 1 minus n u by gu divided by n. This can actually be small n, not capital. Sorry. Let me erase it. NL by GL. Okay, let's see how we get it. So this sigma and FLU are related by this. This is just that, right? This sigma and this expression are the same. NLDS, right? It's just the column density of uh, the ground state, which is this. Now the dependence on frequency is in this line profile phi nu. Now this is a correction uh, due to stimulated emission, right? Uh, but as I mentioned, when your h nu is much bigger than kt, this is small. Stimulated emission, the upper levels are not populated, right? But for 21 centimeter, this is very, very important, as we'll come to it in a bit. Okay, so we will actually ignore this for UV and optical, right? So I mean, this is nothing but, this factor is nothing but e to the minus h nu by kt, right? Kt excitation. This excitation temperature, uh, there are various kinds of temperatures in radiative transfer. Excitation temperature just quantifies the level populations of the U state and the L state relative to each other. That's what excitation temperature is. Okay, so this is sort of the definition of T excitation. Okay. Now, so for Gaussian line of sight velocity distribution, we have tau nu equals tau naught. So tau naught is this optical depth at line center, this frequency. Okay, tau naught times uh, e to the minus u squared by b squared, right? And let me actually tell you, so u equals c times nu naught minus nu by nu, right? So this is just the strength of absorption uh, at different frequencies close to nu naught. So when nu equals nu naught, u is 0, tau nu equals tau naught. When you're away, the strength of absorption is exponentially smaller, e to the minus nu, by this exponential factor smaller. Okay. Now, this b is nothing but square root of 2 times sigma v, huh? Oh. Okay. So we can actually deal with velocity or frequency. They are all one-to-one mappings because of this relation, right? And you note that u positive u greater than 0 is redshift. So that sort of is fine. So uh, positive u means nu is less than nu naught. So be careful about that. Okay. Right. So recall that so let's just write tau naught. The which one? This one. Yes. Yeah. So these are all numbers, right? E is a fundamental constant, MEC, they are all numbers, so they just come out of the integral. What gets integrated over is NL ds. Good. So they're all numbers. Uh, yeah, absolutely. NL is nothing, it's this column. So this is just NL times ds. This is the column density. So capital N is a column density, small n is number density. Small n times ds integral is the column density. Yeah, do not need to assume it to be constant. That's correct. But here, essentially, when we write it like this, we are assuming it constant, but does not matter. That the second this stimulated emission correction is small for this particular case. Okay, let's write tau 0. This is equal to square root of pi e squared by MEC times NL FLU lambda LU by B. And I've sort of ignored the stimulated emission part. So this is just this guy written for nu equal to 0. If you recall, the expression for phi nu for the Gaussian line profile, phi nu equals 1 by square root of 2 pi delta nu. Delta nu is this uh, uh, width of the line profile, and it's related to the velocity dispersion. So this is equal to e to the minus nu naught squared by twice delta nu squared. Right. And so, yeah, from here, you can actually see that delta nu by nu naught equals um, sigma v by c. Right. This is just the Doppler. As I said, the frequency to velocity is a one-to-one mapping. So by substituting delta nu equals sigma v by c, we get 1 by b in the denominator, right? Do you see how you get this 1 by b here? Because there is phi nu, and now you are evaluating at this at nu equals nu naught, which gives you 1 by square root of 2 pi delta nu, and delta nu is nothing but nu naught by c sigma v, and this sometimes this b is used instead of sigma v, and b is nothing but square root of 2 times sigma v. So if you plug that in, you actually see this 1 by b. So the important thing to notice here are there are two things to notice. One, that the line center optical depth depends on this combination, column FLU and lambda LU, right? So you can have the same strength of line center absorption if you have a strong transition with a small column versus a weak transition with a high column. You will get the same absorption. Now, the other thing to note is that tau nu, the line center optical depth here at the line center is proportional to 1 by B. So, hotter the gas is, the smaller tau naught is, right? Uh, the same absorption is spread out over a higher velocity range. So the peak is, the peak absorption is smaller. Okay. So this is actually important to notice. Okay. Now, if you plug in the numbers, what you get is tau naught is equal to 0.76 times NL by 10 to the 13 per centimeter squared times FLU by 0.4164. This is oscillator strength for Lyman alpha. I've sort of normalized all. So these are actually from Drain's book, these formula and stuff. And generally, it does not have typos, which is great because it has a lot of very useful formulae. So this is this lambda LU by 1215.7 angstrom. This is Lyman alpha transition wavelength, and this is 10 kilometer per second by B. So 10 kilometer per second corresponds to 10 to the 4 Kelvin gas. So ISM, as we will actually talk about later, generally has gas at 10 to the 4, warm neutral medium, warm ionized medium, 10 to the 4 Kelvin, or at 100 Kelvin, cold neutral medium. So these are normalized to these typical H1, H2 regions. These are typical. So, and the important thing to notice is that a column of as long as 10 to the 13 per centimeter squared is enough to give you line center optical depth, which is order unity. Even, I mean, this is a very, very small column. The same thing happens for 21 centimeter. If you look at 21 centimeter line, that's a weaker transition. This FLU is like orders of magnitude smaller for the hyperfine transition, 21 centimeter line, which is a forbidden transition. And the column that you need in order for absorb is about 10 to the 20 per centimeter square. 7 orders of magnitude here for B of 1 kilometer per second, because the normalizations are done usually at 100 Kelvin. Okay. Yes. Yes. This is sigma V. This is velocity dispersion, line of sight velocity dispersion. Yeah. Is that okay? Yeah. Yeah. Sorry. Yeah. Yes. I will be normalizing things for Lyman alpha. But it's easy to convert to any other. Like if you know FLUs and the wavelengths, it's easy to do that. Okay. So there are actually, let me first tell you what we're after. We want to, so this W is easy to measure, right? So you have a absorption feature, okay, this is the frequency at which absorption is happening. Let me see how much flux from the continuum is removed. Okay, so basically I take the area under the curve. So I measure W. Even if my spectral resolution is not great, I can know how much flux is missing close to nu naught. So W is an observable. But what I want is something which is physical. So essentially what we are after is this relation between W and the column N L, right? We're after this relation between W and NL. And there are three regimes to consider. One is tau naught is less than 1. This is basically optically thin. The line center is optically thin. So what it means is that this this flux here is sort of, still non-zero. E to the minus tau nu is 1 by E in this case. So you don't have a lot of absorption. So this is the first case. What happened in this case? So in this case, 1 minus e to the minus tau nu is tau nu, right? If tau naught is less than 1, tau nu is less than 1, because the maximum absorption happens at tau nu naught. Okay, so this is this. So your W is equal to, or approximately is equal to, integral d nu by nu naught times this guy, right? 1 minus e to the minus tau nu, which is absorption, is sort of tau nu. So you have this. But if we look at our expression for tau nu, which is here, you will see that uh, this is tau nu, and our tau naught is this. So tau naught is this, tau nu is this. You can actually see that combining these two, tau nu is equal to tau naught times phi nu times b by lambda Lu. Is that correct? Yes. So tau nu is dimensionless. Phi nu, right? So phi nu is 1 by frequency. B is centimeter per second, and lambda is centimeter. So it has the right unit. And you can actually see it's just a trivial combination of this equation and this equation. I don't want to write NL, FLU, and all that. I just write that as tau naught. Okay. So what do we have? The other thing that we have is, right, so we have this. So now we have to just, so this is equal to uh, 1 by nu naught integral d nu. So tau naught comes out, phi nu, and b by lambda Lu also comes out, phi nu d nu. And phi nu d nu is nothing but 1, right? Because that's the normalized line profile. So this is equal to, second, I have missed a square root of pi. You can actually check that there is a square root of pi there. If you look at, so there is a square root of pi here, and there is a pi here. Okay, and all these square root of pi and so on are coming basically because of this 1 by square root of pi, this normalization of the Gaussian. Okay, so there is a square root of pi missing here. Square root of pi. So in the optically thin case, when tau naught is less than or order 1, you have W is equal to square root of pi times B by C times, right, so lambda times nu is C. Because it's nu naught is, nu Lu. So that's just C. So square root of pi B by C times tau naught. This is your, so basically the optical depth is proportional to tau naught, and tau naught is actually proportional to NL. So, and what you can see is there is a 1 by B here. I told you the line center optical depth is smaller if your B is larger, but the integrated integration of that gives you this B. So this B, it does not depend on B, right? This 1 by B and this B cancel. Okay, so this is equal to pi e squared, substituting for tau naught, pi e squared by me c squared nl f lu lambda lu. Okay, so this is your, so this is the expression for low optical depths on this, in this part, and this is independent of b. Yeah, you saw this 1 by b and b cancel out. So this is this linear relationship between w and nl, um, just drawn schematically. So w is proportional to nl, uh, flu times lambda lu. On this part of this relation, this is just linear relation. Okay. Now the second regime is called the flat. So this relation between W and NL is called the curve of growth. Okay. So this is the linear part. So tau naught much less than 1 is the linear part of the curve of growth, because W and NL are proportional to each other, and there is no dependence on B. Okay. So the flat part of curve of growth, what do we have in there? So what happens in the flat part of curve of growth is, so tau naught is less than equal to some tau damp, and it's somewhat greater than about 10, right? There are formulae for, tau between 1 and 10, right? And then it transitions to this flat part of the curve of growth. So what happens in the flat part of curve of growth? Let's see. So you have this continuum. So this is f nu by f nu naught. Now this is your nu naught. Now tau naught has become totally opaque, close to the, but e to the minus 10 is like humongously small, so nothing comes out at the line center. So this one, the shape of this absorption sort of looks like this, right? So there is nothing, basically, essentially everything is blocked here, and it's sort of like a inverse of step function, right? There's 1, 0, 1. Okay, so this is the flat part of curve of growth, and so tau v is equal to tau naught e to the minus u by b, the whole square, of course. So so let's see. So we are actually making this approximation that the flux in this region is 0 and it is 1 here. And what is this full width of half maximum FWHM here? Let's see. So this is a frequency such that 1 minus e to the minus tau nu is equal to half, right? So at this frequency, you have, flux reduction is half. So e to the minus tau nu is equal to half for this frequency. Okay. Or tau nu equals log 2. And tau nu is nothing but that. So delta nu by nu naught FWHM. Basically, this FWHM that I have marked there is equal to twice times U by C corresponding to this velocity. So, right, so this is equal to tau nu equals right. Tau nu equals log 2, which is equal to tau naught times e to the minus u by b whole square. I'm just sort of writing that formula. So I will read off u by b from here, and then I'll just get u by c. So that's what. So that's just 2b by c times log of tau naught by log of 2 square root. Right. So this is nothing but this width. Right. So this 2 times b by c log of tau naught by log 2. So in this regime, when basically you have transmission, zero transmission and transmission, this is called the flat portion of curve of growth, and this applies to this intermediate optical depth regime. Tau naught much bigger than 1, but 10-ish or so, and less than some tau damp. Okay, so in this case, you can actually see. So what is the equivalent width? Equivalent width is nothing but the area under this guy, right? That's nothing but, so the height of this is just 1 times delta nu, right? So delta nu by nu naught. So, I mean, it's nothing but delta nu by nu naught FWHM, right? So that's just equal to that. So equals twice B by C log tau naught by log 2. Now, this is why it is called the flat part of curve of growth. You see, tau naught is here. Tau naught is proportional to NL, FLU, lambda, LU. This is tau naught. And the dependence on tau naught is extremely weak. So there is no so in this regime, there is no dependence on column density. So if we go back to our curve of growth, in this part, in the flat part of the curve of growth, there is a very weak dependence. Square root of log NL. So it's a very, very weak dependence. So that's why this is called the flat portion of the curve of growth. Okay. And there is an explicit dependence on B. Higher the B, higher is the equivalent width. Right? Because the more the spread, absorption is large, so you'll block out more and more light. So this gets split for different values of B. So you have this, you have this. All these are for different values of B. Smaller B, larger B. Okay. What is the third part? The third part of curve of growth is the damped portion of curve of growth. So what happens here is tau naught is greater than tau damp. What happens in this case is, let me actually draw F nu by F nu naught schematically, and then we'll try to derive it. So you have this line center. Now what happens is if you keep increasing your optical depth, of course the line center is totally blocked, but your line profile, uh, the Lorentzian part of your line profile starts transmitting photons. So it sort of looks like this. So you have one, and you have this totally blocked out, but you have these Lorentzian wings. Okay, so these are the Lorentzian wings. Hmm? Right. So the line profile has two parts, right? The one is this Doppler part, which describes the core, nu close to the resonance frequency. But if you're far away from the resonance frequency, the shape of the line is no longer e to the minus nu naught squared. It goes like 1 over nu squared. These are the wings of the line profile. So when the optical depth becomes very high, photons start leaking out of the wings of the uh, line profile. That sort of is the idea. So this requires very high optical depth, like 10 to the 6 or something, extremely high column. Okay, so in this case, so tau nu equals pi e squared by MEC times NL FLU times 4 gamma LU by 16 pi squared nu minus nu naught. This is the Lorentzian. Right? So last time I had told you that far away from the resonance frequency, you will become Lorentzian. Your line profile becomes Lorentzian, and that's what is happening now. And now, so again, we can actually find where this half absorption happens. Where does F nu by F nu naught becomes half, and we can find this FWHM. Now this time with the Lorentzian profile. Uh, so so delta nu by or delta lambda by lambda or FWHM is equal to delta nu by nu. Of maximum. So again, you can think of it in nu space, lambda space, or V space. They are all can be mapped to one to one. Again, this for this guy tau nu equals log 2. So 1 minus e to the minus tau nu equals a half. That gives you this. Now this is this has a different there was a line width in the case of Gaussian dependent on b squared, the velocity spread. Here it does not depend on b. It depends on gamma LU, right? This delta nu would be of order gamma LU, right? The full width half maximum will be something times gamma LU. So if you do the math, what you get is right. So W is equal to integral of d nu by nu naught 1 minus e to the minus tau nu. And if you plug in tau nu to be that, and if you do the math, what you get, nu naught. what you get is W is equal to basically it is also proportional to this full width of half maximum, but there's a pre-factor, right? Because previously it was just 1 and 0. Now it has a shape. So you have to just make sure that you get the proper pre-factor right. Previously it was 1, 0, so it was just a product of the FWHM and 1. This time instead of 1 there is some other prefactor, but of order unity. So this is equal to uh, E squared by, so substituting for tau naught, E squared MEC squared NL FLU lambda LU times gamma LU lambda LU by C, square root of that. And so expressing this in terms of tau naught is, it's just B by C times tau naught. You recall tau naught had a 1 by B in it. Here in this expression there is no B, but if you're writing in terms of tau naught, you have to have a B in front. So this is tau naught by square root of pi gamma LU lambda LU by C. So here you see the B, there is a dependence on tau naught, but it is square root. So the column density dependence the equivalent width is proportional to the column density. So here, now in this expression, there is no dependence on B. And if you just write it as a function of NL, equivalent width versus NL, there is no dependence on B, right? In this expression, there is no dependence on B. So what happens is, in all these cases, this guy is a flatter part, right? So this is proportional to square root of column. Here it was linearly proportional to column density. Here it was essentially independent of column density. Here it is square root of column density. And there is no dependence on B. So what happens is no dependence on B, linear, splits because of B, higher values of B, higher values of dispersion gives you higher value of W. And then again, the dependence on B goes away. Okay, so now the way to use this is you are measuring this and you're trying to get this. So you have to make sure that, so if your absorption is like, if tau naught is small, then you can use the linear part of the curve of growth. If your line is saturated, that is, the line center optical depth is greater than 1, in that case, you're either in the flat part of the curve of growth, then measuring NL is very, very difficult, right? Because this is almost flat. So if you measure a W and you have some sort of error on W, the error in NL is huge because it's almost flat. So in the flat part of curve of growth, measuring the column is hard. In the linear part, it's sort of easy. In this part, when the photons start coming out through the Lorentzian wings, you can still get W, you can still get the column from W. Okay, so this is about curve of growth. Yes. Right. So, right. So, I mean, in last class, I told you that the line profile is the convolution of Gaussian, which sort of goes down uh, e to the minus nu naught squared, right? But there's also a Lorentzian. So if you go to high, yeah, so I mean, this was done in last class. So as you go to high frequencies, uh, this convolution basically, in this limit, the Gaussian becomes a delta function, and you just choose out. Uh, yes, basically you're dominated by the Lorentzian rather than that exponential decay. That's correct. I mean, we can consider anything. This L can be any, I mean, it can be atom, ion, or anything. Hmm. Hmm. I mean, see, once you have the level populations, it can be because of recombination, photoionization, whatever. But once you have small nl given, then this applies for any ion. So, for example, you can have absorption of neutral hydrogen due to 21 centimeter. You can have absorption due to neutral hydrogen due to Lyman alpha transition. You can have in the same gas, you can have absorption due to some calcium, Ca plus, which is calcium 2, carbon 3, carbon 4, depending on the conditions, you will have different abundance of different ions. And once you have those ions, a background light will, will have this absorption features at those particular frequencies. Kappa nu. Where is this? This one. Yeah, so kappa nu is just NL times sigma nu. No, 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 no. This is line. Just, bound. We are talking about line transitions, right? In a line transition, you have, a lower state and an upper state. And the absorption is like a delta function, which is described by the line profile. If you're bound free and all those, you don't form a line. What you have is an edge. Right? So this modeling does not apply to bound free transitions. Okay. Um, I mean, these are all like approximate formulae in these relevant things. So there is no real discontinuity. So you can actually get this tau damp. How do you get tau damp? If you equate this expression and this expression, you will get tau damp. Basically, when does this asymptotic formula and this flat formula cross each other? That's what corresponds to tau damp. So there will be no. I mean, if you do it mathematically, there will be no discontinuity. These discontinuities come because of these, like, simpler ways of doing this algebra. Okay, cool. So very important, actually. This is practically extremely important trick, and this applies to any absorption line, molecular absorption line, uh, atomic lines, oxygen 6, X-ray lines, infrared lines, whatever. This technique applies to any bound lines. Okay. So now we'll actually do 21 centimeter line. So this is 20, oh, 21 centimeter H1. I don't know why has this become slow. Should I start a new? I don't know. Last time it didn't quite help. Uh, Let's see. Oh yeah, it's faster. 21 centimeter H1 radiative transfer. Okay, so this 21 centimeter line is an extremely important line uh, for the ISM. Let me actually tell you. Oh, yeah. So this is the hyperfine. This is the hyperfine uh, transition of neutral hydrogen, right? So, if you look at the hydrogen atom, and it has the electronic levels, n equal to 1, n equal to 2, and so on, and then there is this LS coupling, right? So uh, these electronic levels get split due to various couplings, right? LS coupling is this what gives you fine structure splitting. The coupling in the so you have orbital motion of electrons and you have spin of electrons. The orbital of motion of electrons produces a magnetic field in which the spin of the electron interacts, and the energy is mu dot b. And if you do the sort of calculation, you get due to this you get this uh, fine structure. Okay, but due to the spin of the proton, so a neutral hydrogen has a proton and an electron around going around. So this interaction between the proton spin and the electron spin gave rise to this hyperfine splitting of the principal levels. Okay, so this is the hyperfine transition, and so this is like how we can actually represent it. So this is L and this is U. And L and U we are using generally, right, for any transition. So in this case, in the ground state, so you have electron and proton have opposite spins. In that case, energy is minimum. In this case, you have their spins are aligned, so it's a higher energy state. Uh, and the degenerate, so this has S equal to 0, right? So the spin, if you add the spins of electrons and protons, in this case, it's 0. Here, spin equals half plus half, which is 1. And the degeneracy is 2s plus 1. So this is Gu equals 3, Gl equals 1, right? So uh, the degeneracy factor of the upper uh, level is 3, and the lower level it's 1. The Einstein A coefficient, AUL, is about 2.9 into 10 to the minus 15 per second, which is about 11 mega year inverse. So what it means, I mean, it's a very, very, very weak transition. What it means is that if you have uh, hydrogen in this upper hyperfine level, if you have one hydrogen atom, it takes 10 mega years to spontaneously decay to the lower state. Whereas the Lyman alpha, so this is a forbidden transition. The Lyman alpha transition is an allowed strong transition, and that would have like 8 orders of magnitude or 7 orders of magnitude higher value of A. This was reflected in this column density that gave you optical depth order unity. I told you that it's 10 to the 13. At 10 to the 13 column density, the line center optical depth becomes order unity for Lyman alpha. But here it is 10 to the 20. So that 7 order of magnitude essentially comes from this weakness of A. Okay. Okay, good. Now, if the radiative decay time is so long, why do we even see 21 centimeter line? The reason we see 21 centimeter line is there are so many atoms out there. So if you have like 10 to the whatever, 27 uh, atoms doing this, even though each one of them takes a long time to do this transition, there are so many of them, you at all times you get significant radiation. It's because of the abundance of neutral hydrogen. Uh, right. So this energy gap corresponds to nu equals 1420.4 megahertz, and it's 1.4 gigahertz, right? That's why a lot of radio telescopes work near 1.4 gigahertz so that they can do 21 centimeter in the nearby universe. And that's why these guys at RRI are, trying to go to very low frequencies like 100 megahertz in order to see 21 centimeter stuff at redshifts of 20, right? So because at high redshifts, the frequency 1.4 gigahertz gets shifted to 100 megahertz. Okay, so this is fine. Wavelength corresponds to 21.106 centimeter, and delta E by K is equal to 0.06816 Kelvin. Right, so this is sort of the delta E by K is like a temperature. The energy difference by the Boltzmann constant is about 0.06816 Kelvin. So basically, delta E is tiny compared to the typical excitation temperatures of hydrogen gas. So what it means is that e to the minus h nu by kt factor, this nu by nl equals gu by gl e to the minus h nu by kt excitation, that exponential factor will essentially be 1. This is what it means. Okay. So nu by nl equals gu by gl times e to the minus h nu ul by kt. And as I mentioned, this is basically 1. This is equal to 1. For all typical conditions, h nu is much smaller than kt. So this is nothing but 3. Right? That's just the degeneracy factor, 3 by 1. So what it means is nu equals 3 by 4 nh, and nl equals 1 by 4 nh. Small n is the number density of neutral hydrogen. So 3/4 of neutral hydrogen atoms are in the upper state and 1/4 are in the lower state. Okay. So what about J nu is equal to? So this is emissivity, right? So energy emitted per unit frequency, per unit time, per unit volume. So this is equal to Nu times AUL by 4 pi times H nu UL times phi nu. Let's see. So A is, so this 1 by 4 pi comes because of the solid angle. So it's an isotropic emission. So per unit solid angle gives you 1 by 4 pi. Right. So this is energy per unit volume, per unit time, per unit frequency, per unit solid angle. Right. So this is also related to I nu, which is per unit area quantity. So they are all related. So you should be very conversant with the basic radiative transfer. So this is probability per unit time. This is number density. This is energy 1 by frequency. So you can actually see it has the correct unit. This is energy 1 by frequency, 1 by time, 1 by solid angle, and 1 by volume. Right? Always make sure that the units are correct. So what does it give you? So this is equal to, so Nu is nothing but 3 by 4 times Nh. So this is approximately 3 by 16 pi AUL H nu UL and H1 phi nu. What about, so this is the emission. What about absorption? What about kappa nu, absorption uh, coefficient, kappa nu? So this is equal to NL times sigma LU. Right? See, kappa has a unit of 1 by length, right? Uh, so mean free path is 1 by n sigma. So essentially, alpha or this kappa is 1 by the mean free path. That's why it's n sigma. Okay. So this is this. But so this is just due to absorption. But as I mentioned earlier, the stimulated emission is absolutely important in case of the 21 centimeter line. So this is due to stimulated emission. So stimulated emission reduces absorption. It's sort of opposite of absorption. It sort of uh, it depopulates the upper you know, I mean, it's sort of opposite of absorption because you're emitting, but your emission is proportional to U nu. You need a background radiation in order for stimulated emission, but it produces photons rather than absorbing photons. So it has a negative sign uh, compared to absorption. Okay. And the sigma and A's and oscillator strengths, they are all proportional to each other. So if we express this in terms of AULs, right, what do we get? We get NL GU by GL times AUL by 8 pi lambda UL squared phi nu. I mean, these are all dependent on frequency. Phi nu times 1 minus NU by NL times GL by GU. Previously, I had ignored this, but now I will not. I cannot. The stimulated emission is absolutely important. And this, the definition of this is just e to the minus h nu UL by KT excitation. So excitation temperature, or in 21 centimeter language, the spin temperature quantifies the level populations. And the populations in the upper state and the lower state, like this. So if we plug that in, and of course h nu is much less than kt, so we can, this is just 1 minus e to the minus x, where x is much less than 1, and that just gives us x. So this is equal to uh, 3 by 32 pi AUL HC by K T spin. T spin and T excitation are the same. In 21 centimeter, the excitation temperature is more commonly known as the spin temperature. So this is the same as that. Times lambda UL N H1 times phi nu. But it's, whatever I've done is just expanded this and I wrote NL as 3 by 4 NH1 or NH, and I got this 3 by 32 pi, because 3 by 4 times this is that, AUL, GU by GL is essentially 3. Right? The degeneracy of the two levels, and so on. So this is simple. So the important thing to note is this 1 by T spin. Right? The absorption coefficient of the gas with lower spin temperature is much higher. cooler gas or lower spin temperature gas absorbs more efficiently for 21 centimeter. It's important to pay attention to this. Okay. Now, this is such a weak transition that we don't really think, it's almost impossible to have tau naught of 10 to the 6 or something, right? So there's Lorentzian wings and what was this? The damped part of the curve of growth is not almost never relevant for H1, because that is only when tau greater than tau damp, right? Very high optical depth. Usually the strength is so weak that essentially that is never important. So what we have is, so we have the line profile phi nu equals, we can just choose it to be Gaussian, because the Lorentzian part is almost never important. So phi nu equals 1 by square root of 2 pi c by nu ul 1 by sigma v e to the minus u squared by twice sigma v square. So yeah, you have to be used to b, sigma v, delta nu, all those are equivalent. A lot of this stuff is about just understanding what these things mean. The other part is actually simpler. Okay, so this is the line profile for 21 centimeter. Right. So what do we want to do? So we want to actually substitute this phi nu from here. What do we get? So your kappa nu equals 3 by 32 pi 1 by square root of 2 pi a ul lambda ul squared. So c by nu ul is lambda ul. So that's what I'm using, by sigma v h c by k t spin n h1 times e to the minus u squared by twice sigma v squared. So, you should just be aware that so nu minus nu naught by nu naught equals, or nu naught is nu ul, right? This is equal to sigma v, no, sorry, sigma is just the width, so this is u by c. This is equal to minus u by c, because nu is less than nu naught for u positive. Okay, so whenever I write e to the minus u squared by 2 sigma v squared, what I'm assuming, because this is a function of frequency that I'm talking about, so you should just mentally substitute this u as this. Okay. And what about this is your kappa nu. What about tau nu? Tau nu is integral kappa nu ds. If we do that, what do we get? We'll have to just integrate this over the path. This the spin temperature can depend on your location along the line of sight. You can have some lower excitation temperature gas, higher excitation, and so basically both of these, this and the spin temperature, are the ones which will get integrated over. Like this is independent of the line of sight. This is independent of coordinate along the line of sight, right? This is just nu minus nu naught. It does not depend on that. So what do we get? What we get is let me just plug in the numbers. So 2.19 times n h1. So here, so going from here to here, I have assumed that I have a constant density and a constant spin temperature. Otherwise, I will have to take care of this 1 by t variation along the line of sight. Or what you can do is you can interpret this equation in a different way. So let me just write down. So this is 10 to the 21 per centimeter squared times 100 Kelvin by T spin kilometer per second by sigma v e to the minus u squared by twice sigma v squared. Right. So my NH1 by T spin, which is a function of S ds, is equal to NH1 by T spin. This is basically my definition of this T spin. This is like a harmonic average of temperature, spin temperature along the line of sight, right? It's like this one, right? So this is nothing but N H1 ds. So this T spin is like a harmonic mean, right? 1 by T equals summation over 1 by Ti. Right? The lowest temperature is what contributes the most to the absorption. So if you have gas at 100 and 1000 Kelvin, the 1000 Kelvin gas will not absorb much. It will be the 100 Kelvin gas. So you will your spin temperature, the effective spin temperature for your absorption will be closer to 100 Kelvin because of this. Okay. So if you have optically thin clouds, basically tau naught is less than 1, optically thin cloud, or optically, basically I'm making this less than 1, and this value is less than 1. So my NH1 is less than 10 to the 20 per centimeter squared T spin by 100 Kelvin. You see, this is proportional to T spin now, because higher the T spin, less absorbing the neutral hydrogen 21 centimeter gas is, times sigma v kilometer per second. This is the other thing, right? If your velocity dispersion is large, tau naught is small, right? Remember, your phi nu, the Gaussian phi nu, had 1 by b in front, and that's this guy. This is 1 by b, and when you calculate this critical column when tau becomes 1, it's proportional to b. Higher the b, the critical column is higher. You need a higher column for it to become optically thick. So for optically thin clouds, we can actually neglect, if tau naught is much less than 1, you can neglect absorption. In that case, what do we have? We have I nu equals I nu naught. So some background, so you have some region, you have I nu naught. This is a column which is emitting and also possibly absorbing, but I'm actually neglecting absorption. So this is just I nu naught plus. So you will have contribution of radiation from all these things which will be emitting. So you have integral J nu ds. So absorption is totally neglected here. Okay, so J nu is this emissivity that we encountered. So this is equal to I nu naught plus 3 by 16 pi. I had written an expression for J nu earlier. Here it is. Here. I'm just going to substitute that. So 3 by 16 pi AUL H nu UL pi nu times N H1. So integral of I nu minus I nu naught d nu. Right, so this is just the emission. This is just the emission due to the H1 cloud. This I nu minus I nu naught is just this guy, which is emission due to the H1 cloud. This is equal to, now we are just going to integrate over the line profile. Everything else is a constant. So if you integrate it over line profile, you get 1. So this is equal to 3 by 16 pi AUL H nu UL times NH1. So you can actually see this is the this is the this is the emission. The emission that you see from a 21 centimeter cloud is proportional to the column density of that cloud. If you neglect the absorption due to that cloud, so emission is proportional to the column density. 21 centimeter emission is proportional to the column density of neutral hydrogen. This sometimes is also expressed in terms of the antenna temperature. Antenna temperature. So there are various kinds of temperatures in radiative transfer. Something called antenna temperature or brightness temperature. Both are sort of used interchangeably. There is effective temperature. Then there is spin temperature, excitation temperature. So you have to be aware of that. If you're not, look at Rybicki enlightenment. So antenna temperature basically quantifies this. Antenna temperature is proportional to, so T antenna is equal to I nu times, so you have to convert it into, so twice, so nu squared. Just a second. So basically, this is how in the Rayleigh Jeans part, I nu equals twice kT by lambda squared, right? The intensity. So this is basically the definite in the Rayleigh Jeans part. The intensity. So this is sort of this is how you sort of define your antenna temperature. So antenna temperature is this is nothing but C squared nu squared. So antenna temperature is I nu times, sorry, I'll just get rid of this. I nu times C squared by nu squared KB. So this is your antenna temperature. So sometimes you use this to quantify the specific intensity. Okay, so the last topic is determining MH1. We want to determine what's the mass of my H1 cloud from which I am observing 21 centimeter emission. So determining MH1 from the flux. So we have some flux measured in 21 centimeter. We want to measure the amount of H1. So we are assuming optically thin cloud. It sort of makes sense that if you have an optically thin medium, the luminosity will actually be proportional to the total mass. The more mass you have of an optically thin gas which is emitting, the more light it will emit. Right? Unlike an optically thick emitter, like the sun, the luminosity is proportional to the area and T to the 4, like sigma T to the 4. For an optically thin emitter, you can actually see through the entire volume. So the luminosity is proportional to the total mass. Okay, and that's what we are actually going to use to get the total mass of H1 cloud. Okay. So I nu is equal to 3 by 16 pi, optically thin. As I said, you can get absorption in H1 also, but not all clouds. It's only rarely that if your line of sight goes through some very dense region, that absorption is important. So 3 by 16 pi A UL H nu UL phi nu NH1. So N H1. So this already we had written, right? This is for I nu. Like we are ignoring this I nu not. We are assuming there's no background emission. So this is nothing but that. This is integrated over nu, but this is what we have. 3 by 16 pi AUL H nu UL. Okay. Now, so how do we get mass of the gas? So you have, this, say, H1 cloud, you are observing it, and this is the expression for specific intensity. This is your solid angle, let's say, delta omega, that the cloud subtends. We are assuming that this cloud is sort of uniform. Okay. Right. So what is this? This is energy per unit time, per unit time, per unit frequency, per unit area, per unit solid angle. Right. So if you have an emitter, so this is the area of the emitter. This is the solid angle subtended by the emitter. And this is frequency is right. So what is d omega or delta omega? This is nothing but, and you have a telescope here, right? So with some area A, let's say, let this be a dA telescope. Okay. Right. So when we are considering radiation coming from this, this dA is the area of this emitter, and this d omega is the solid angle subtended by the telescope. So this combination dA d omega is d area of the telescope times d area of the emitter divided by the distance between them squared. This is the distance. Okay, distance is of course very, very large, but we are not taking it to be cosmological. You can take it to be a cosmological distance, and then there'll be 1 plus z factors. We are not going into that complication. So this is this. So dA times d omega is nothing but this. What we are measuring is flux, which is this guy, right? So dE by dt by, so this is the flux measured by a telescope. Energy per unit area of the telescope, per unit frequency per unit time. So we have the expression for this. So let's just write it F nu. Right. So the F nu divided by the area of the cloud that is emitting times the distance squared. So F nu is nothing but dE by dt by d nu by dat. Right. This is equal to this expression. Right, this flux is flux per unit frequency. So we are actually looking at flux coming at every frequency. We have not integrated it over. Right, so F nu times d squared is equal to 3 by 16 pi times AUL H nu UL times pi nu times NH1 times the area, right? That's nothing but column times the area is what? Total number of H1 atoms. Column times the area is the number of H1 atoms, neutral hydrogen atoms. Right? So number of neutral hydrogen atoms times uh, uh, mu mh divided by mu mh. Now this guy is the total mass of the H1 cloud. Mu is mean mass per particle. Right? You know about mu. Mean molecular mass. This is actually usually known as. So this is the mass of H1 cloud. So we have the expression for mass for H1 cloud. So mass of the H1 cloud is equal to, and we can just also integrate it over frequency if we want. The phi nu is the only nu dependence, and that gets integrated over. And F nu d nu is nothing but flux in energy per unit area per unit time. So mh1 equals 5 times 10 to the 7 m sun times 10 distance by 1 megaparsec. I mean, 1 megaparsec is still redshift 0. F observed by Jansky megahertz. So you actually can see it from here, right? That flux is, so this mh1, which is this guy, number of atoms times the mass of each particle. This is the total mass. So total mass is proportional to d squared, proportional to total flux of 21 centimeters. So this is what you have. Now, if this is at a cosmological distance, this gets replaced by dl, the luminosity distance. Okay. Now, I'm not going to go into how, but this is the answer that you get. Oh, you tell me. At what distances do you become cosmological? So see that V equals HD, right? This is 70 kilometer per second per megaparsec. So, but you have to become V order C in order for it to become cosmological. The recession velocity has to reach C. So the distance at which that happens is about C by 70 kilometer per second. 70 kilometer per second. So that's 3 times 10 to the 5 kilometer per second. So that's about a few hundred megaparsecs. Okay. Yeah, these questions you should be able to like even calculate in your sleep, like when it becomes cosmological. And it's not like it's nothing. You just had to use H naught. Okay, so this is how you determine H1 mass if you are able to measure the flux. So we are done with the class. Next time we'll actually be starting H2 regions. So photoionization and recombination and related things. Okay.